Okay, so welcome back everyone to Scrap Paper and Philosophy. And I'm gonna begin by, well, I think the elephant in the room is this, right? I think this the unit of the dimensions of the wave function are poorly understood. This 1/length is what is being taught on, I believe, the 5th or the 6th, maybe the 7th, because I think I only saw 10 lectures of the course. So I think it's the 6th or the 7th lecture that the dimensions are derived to be the square root of 1/length. But of course, that's a complex number, and we're conjugating it, and so the interpretation would be 1/length, which is force over energy. Or if you prefer, depending on the context, the square root of force over energy. But that's one thing we ought to look at because we want to understand it. But what I want to talk to, uh, what I want to talk, the subject I want to talk about today is, I mean, right now is this. Uh, it's a fact of life that, well, before I talk about this, let's look at a picture of a circle in 2 dimensions, right? What do we gain when we move from, by the way, a point is 0 dimensional, right? Newton told us that. We know that a long time ago. Descartes would have been able to say the same thing, I guess. So a point is 1 dimensional. A line, a point is 0 dimensional, right? A line is 1 dimensional. And what do we gain from moving from a 1 dimensional world to a 2 dimensional world? Well, one of the things we obviously gain is circular motion, right? We can write the equation of the circle in 2 dimensions. There it is right there. Interestingly enough, another thing we gain is time, because time, in a sense, the essence of time is circular motion. This is the period of the pendulum right there. And if you look at this equation for time, which we've already seen, it matches the period of a pendulum. But I didn't have to demonstrate this computationally, which I haven't, because it's we can demonstrate it graphically, right? What we gain from 2 to 3 dimensions. Before I move on, if you have motion in 1 dimension, you need 2 variables. You need x for the displacement, and you need t for time. So we can actually verify that, by computational intuition, that 2 dimensions gives us time, 1 dimension does not. But what do we gain from going from 2 dimensions to 3 dimensions? And what do I mean by the non-stationary random walk? Well, this was taught to me in a math class, and I don't remember if the professor proved it right there, but it's a topic in statistics, and it's very interesting. There's probably a whole course on this topic, because it's such an interesting little fact of life that's very rarely known. So I think I should share it with you. And let me use scrap paper, which is nicer, because I don't want these lines here. So we have a random walk in one dimension. You flip a coin, and if the coin gives heads, you move one step to the right. If the coin gives tails, you go one step to the left, and you're always moving along this line. That's a random walk in one dimension. If you're going to look at the starting point, well, actually, this is one-dimensional world. So there's a starting point right there, and you can only go this way or that way. And if you calculate the probability over an infinite number of coin flips that you're going to end up somewhere, you are likely to end up the same place that you started. So in two dimensions, it would be the same thing, except you're flipping the coin, you're tossing the coin twice. One to assess whether you move right or left, the other to assess whether you move up and down, because up and down is possible in this world. And so you only need one coin, but you're tossing it. And that's a random walk in two dimensions. And I don't remember the proof, but I'm pretty sure that you're going to end up at the origin where you started. And now, in three dimensions, well, in three dimensions, you can start at this origin right there. You can have 6 coin tosses at a time. We have 6 coin tosses at a time. This one we assess whether we move right or left. This one we assess whether we move up or down. And this one we assess whether we move, well, let's see. I said up or down. I said right or left. So we assess whether we move out of the page or into the page. One step. 6 coin tosses, one step. Then we go to the next, and so forth and so forth. I believe, I'm not sure, I have to look into this, but I believe, strongly believe, because this is such a notable fact that it was said to me more than once. I mean, I think I read about it, and I think it was also mentioned by a math professor. If you calculate if you do the simulation for the random walk, well, why don't we go ahead and do that? But if sometime, it's very easy to code. But if we code the simulation for this random walk, I believe that we're actually in motion. We're not over an infinite amount of time. We're not at the origin anymore. We're getting somewhere. And well, I actually have one more topic, but trying to do short videos. I'll continue soon.